next speaker is Michela Carlotta Massi from Politecnico di Milano.
Yeah, hi, good morning.
Hi, and she's gonna talk about EEG embedding and cross-subject channel selection algorithm for trial classification. Please, Carlotta. Thank you. Go ahead.
Can you see my full screen?
Yes, perfect.
Okay, so good morning, everyone, and thank you for being here. I am Michela Massi, a PhD student from the Department of Mathematics at Politecnico di Milano, and I would also like to thank you for the chance to talk to you about this work, which was developed in collaboration with my PhD supervisor, Francesca Ieva, at MOX Statistics in the Laboratory for Computing and Scientific Modeling of the Department of Mathematics at Politecnico. Di Milano. And as you can see here today, that is under ongoing development, but that it is providing us with promising results, which I'm pretty happy to share with you today. So the talk today will start by briefly introducing our motivating research objectives, and then I will deep dive into the different aspects and the different components of the algorithm, trying to give you an idea of the rationale behind the choices that we made in its design. Then I will present a case study that served us as a good platform to prove empirically some of the concepts I will discuss in the following. So to start with, the context of our study is that of automatic digital processing of EEG signals for classification or prediction tasks that has, of course, several very different applications, like the detection or the prediction of health statuses, sleep states classification, and many other. Of course, they all have their peculiarities. But in most of these cases, the acquired EEG signals are generally multi-channel in nature. So they require subjects under study to wear several electrodes on their scalp. And this multi-channel nature may actually lead to long setup times and sometimes also cause subject inconvenience. Moreover, if we look at it from a modeling perspective, it has a certain level of computational complexities when trying to process signal data for prediction or for classification task with any kind of modeling that might be machine learning or statistics-driven modeling. And this might be especially problematic, for example, if we wish to develop portable medical support systems that should in principle rely on computationally efficient prediction algorithms that use the least number of channels, of course, for computational requirements, but also for better portability and for lower energy consumption that would grant longer use times. However, so we can say that from both a clinical and a mathematical perspective, reducing the number of channels may reduce the redundant information that we introduced in any following model. It might improve the signal to noise ratio, and it might also positively affect all the aforementioned medical real applications in the development of any clinical device. However, by studying that as statisticians, which is what we actually are, we noticed that when talking about Eeg channel selection, most of the literature in many fields designs methods for subject-specific channel selection. And of course, this makes a lot of sense since EEG presents a strong inter-subject variability and variability also between trials and so on. So it really makes sense for it to exist a huge literature on subject-specific channel relevance. But finding a way to select a generalizable subset of channels with a good enough classification performance would definitely be of help, for example, in the case of devices development. So we were fully aware of all the complexities that we were going to face, but we tried to contribute to this specific objective by developing an algorithm that is what I will actually introduce today. So For brevity, we gave it a name which is Ernest, that stands for Eeg, Embedder, and Channel Selector. And as you see from the schema on the slide, it is composed of several modules. Each presents its peculiarities and specific objectives. And I will try now to detail a bit of each of them, and especially try to make you understand why we made the specific choices around each of the components that we included in the algorithm. But first of all, notice that the algorithm works on a set of signal recordings that we will in general today define as trials, which are basically fixed length signals recorded simultaneously from several electrodes. So of course, depending on the specific setting, it might be one stimulus of a visual or auditory event related potential, or an epoch within a motor imagery experiment, or a chunk of recording for patient's classification, and so on. But in this case, so far, we're working with fixed length signals recorded simultaneously. So the final objective, of course, is that of the classification. So the classification of those trials, meaning that we have a label associated to each of the trials, specifically to the trial or to the subject, in case we're trying to classify all trials belonging to the same subject class, let's say. And this is actually very important for our algorithm, as Ernest's first component is the feature extraction module that performs a channel-specific mapping or feature extraction in a supervised fashion, and that is why we need the actual labels, to maximize inter-class separability from the extracted features. In practice, we make this process end-to-end by exploiting a representation learning method channel by channel. So you see here a mathematization that has only the scope of saying that irrespectively of the representation learning method that we introduce and we use in the algorithm, any model can be basically seen as an encoder function with its parameters that then is encapsulated into a classifier function. And altogether, they are parameterized by gradient descent of the loss function that, of course, is tailored around the specific task at hand. And this procedure, this way of seeing the two functions actually allows us to save an important information for our algorithm, which is the parameters of the encoder function only, that for each channel maps the signal to an embedding space of lower dimensionality that is informative with respect to the target, because we are, I remind you that we are learning the parameters in a supervised way. So as representation learning method, at the moment, we chose the shallow one-dimensional convolutional neural network, as they were proven powerful feature extractor in several working with signal data, and in several works working with EEG signals specifically as well. But we actually ran, in a preliminary study, we ran a comparison of many different methods from the representation learning literature, but also much simpler methods like PCA or other representation methods that do not require computationally intensive, let's say, parameterizations. But we actually realized that one-dimensional convolutional neural networks were the one that eventually provided the best generalizability across subjects, which was the thing that we had in mind as a final objective for this algorithm. So moreover, these kind of models, when if properly designed and correctly parameterized, let's say, are very interesting because they are end-to-end, and so they potentially allow us to avoid cumbersome preprocessing procedures, which are oftentimes knowledge intensive and task specific, and also, of course, time consuming. And moreover, this specific model, compared to other representation learning models, has a smaller number of parameters, needs a smaller number of parameters because of parameter sharing architecture, and is less prone to overfitting if you properly regularize it, which is another good aspect when we think that we're trying to make a cross-subject feature extraction. So far, in the current design of the algorithm, as I mentioned, we are parameterizing a set of different one-dimensional CNNs independently. The rationale of this idea is the fact that we're trying to maximize the information extraction from each channel. Plus, having a separate sets of parameters allows us to manage easily the subsequent channel selection, and also manage the fact that in the future, in a real setting application, one may decide after channel selection to record signals from less channels. So this kind of approach is able to manage easily the missingness of channels. So after parameterization, the embedded channel-specific training trials are then concatenated so that we recover actually the multi-channel view of the trial. But while doing that, we also reduce the intrinsic dimensionality of the data and of the problem itself. So despite treating each channel independently, the information contained in the multi-channel view is recovered and will be very relevant in the subsequent passages, especially in the channel selection, in the proper channel selection module that I will introduce now. So we have these trial vectors that are, let's say, composed of concatenation of embedding of channel-specific signals. And once we obtain those trial vectors, we feed it to the channel selection model that seeks to find the channels, so that set of features within the trial vectors that are more relevant to discriminate between the classes. In order to do that, we exploit an ensemble of deep sparse autoencoders. To make it very simple, let's say that autoencoders are basically neural networks that are trained to reconstruct their input after dimensionality reduction in the bottleneck layer. So in this ensemble approach, each component is an autoencoder, and each autoencoder component is trained on one class only, and then tested on both classes. What we would expect is that the reconstruction error on the class never seen during training is higher, and especially on the dimensions of the input vector where the two classes differ the most. So by exploiting autoencoders in this identification of the relevant features in the trial vector, we are basically recovering the information on the complex nonlinear relationship between the channels. So the multi-channel view that I was mentioning before, we are not losing it, but we are exploiting it during the channel selection to recognize what are the features most relevant to separate the classes. So that would be, I mean, using just one component would be a good indication of the dimensions of trial vectors that are associated to the most relevant channels. But actually a single autoencoder might provide variable results due to the data, the model design, the local search of parameters. And of course, this kind of very large models, in our case, they're not really that large, but in any case, they have an intrinsic variability in results that we wanted to account for. So for this reason, we opted for an ensemble approach that is basically meant to cut this variability and obtain more robust results. So to foster, however, diversity among the ensemble component, which is very important to make an effective ensemble approach, we designed our algorithm so that each component would be trained and tested on a different sampled subpopulation. And then we added the sparsity constraint on the bottleneck layer that basically makes the least number of nodes in the bottleneck layer activate conditional on the data that it is seeing, which is different because, as I said, each time we sample a different population for training and for testing as well. So in the schema that you see there below, each observation, so each dot is a trial vector that is fed to the ensemble. And once we have repeated the training and the testing a large enough number of times, we result with a matrix of reconstruction error that we collect each time. And from that matrix, we use that matrix to compute the metric on which we will select the most relevant channels. Indeed, first we compute the reconstruction error aggregated by channel and by class, meaning that we average the reconstruction error by class on the subvectors associated to each channel. So as you see from the slide there, we make the average reconstruction error divided by class for each of the dimensions with the same color, let's say, which are the ones that are associated to the same channel. And then once we have this averaged by class and by channel reconstruction error, we can compute the delta. So the delta reconstruction error by channel, and that is actually the metric that we use to rank order the channels and eventually come up with the selection of the top K most relevant channels to discriminate between the two classes, so the negative and the positive class. One thing that I wanted to mention is that actually this algorithm was here modified from a previous work of ours for feature selection instead of channels. So at the time we were interested in the features, not in the group of features that are more relevant. But actually that algorithm was designed in order to be very robust to class imbalance, which is meaning that basically it should provide reliable feature selection also in case of very imbalanced settings. So class 1 examples are very few compared to the 0 or the null class. And this might actually be the case of some real life application of EEG signals as well. And this additional aspect is makes it even more interesting in this context. So here you see again our algorithm, the schema of the full algorithm. That what I just described so far is the training phase. So starting from the trials, so the trial signals, we go through an embedding phase. We transform each channel signal into a single trial vector. We feed it to the autoencoder ensemble and we select the most relevant channels. Now, if we want to perform classification on new trials from new subjects, potentially, we can just extract the parameterized models, so the functions, the encoder functions. We can extract them only for the selected channels because we don't need the others. We can embed the new signals. We can create new trial vectors that are smaller in size and that are highly informative with respect to the classification task, because they are embedded in a supervised way. And these new smaller test trial vectors can be fed to any type of classifier, because we actually are doing what is called a filtering selection technique, meaning that it is really classifier agnostic. Therefore, after that can be introduced any kind of classifier for the specific task that would maximize the performance on the task at hand. As anticipated, at the beginning of this talk, we tested our Ernest on a case study that was interesting to us because it came, of course, from a freely distributed database with a sufficient number of subjects and also a large enough number of channels that would motivate channel selection. And moreover, it is about the early detection of the predisposition to alcoholism that actually is a task that might benefit from a generalizable channel selection, as it might be, for example, a useful component of an automatic clinical decision support system. So new patients arrive and we have a clinical support system that helps us, that might inform a clinician towards the possibility of alcoholism predisposition for this new patient. So sorry, in this application, the objective, as I was saying, was that of detecting trial of alcoholic subjects from visually evoked potential EEG signals. We had 122 subjects that were equally split between alcoholics and control subjects. And each of those subjects performed 120 trials each. And each trial was recorded across 64 electrodes or a channel that then were, after removing the reference channel, were just 61 channels. And each trial had a dimension of 256 features.
You have five more minutes.
Yeah, sure, thank you. So subjects were exposed to two picture stimuli appeared in succession. A first picture stimulus S1 was followed by a second stimulus S2, either matching or non-matching the first picture. But to make the task a little bit more complex, we tried to classify trials only on the basis of the evoked potential of the first stimulus S1. So note that, of course, in this case, the label assigned to each trial comes from the subject itself. So the subject was either alcoholic or control, and each of the trials that were associated to him had, of course, the same label. We splitted our subjects in two very separate sets. So in 102 subjects were used for earnest training and to select the channels, while 20 independent new subjects with all their trials were used for testing. Here you also have some details about the architectures and the hyperparameters that we used. But of note, I would just like to show you that we kept 1D CNNs as shallow as possible, because of course we had in mind that the overall algorithm needed to be as lightweight as possible. And we embedded each signal to only 4-dimensional embeddings. As for the ensemble channel selection model, we used 30 autoencoder components that actually can be easily trained in parallel to cut computational time. As you see here, we have some preliminary results with this case study in terms of outlook and accuracy. And looking at them at the moment, they look really promising, especially if you consider that those were obtained in a cross-subject experimental setting, meaning that the performance you see there is obtained on totally new subjects, averaged over 10-fold cross-validation. And we tried to compare to other works that in literature were working with this kind of data, and we actually couldn't find any example that was comparable in terms of fully subject-agnostic classification. So here in the table, you see we use the different classifiers, as this is, as I mentioned, a filtered channel selection algorithm, and you can use any type of classifier. And each row corresponds to the number of channels that we used to construct the trial vector for classification. So 4, the dimension of the embedding, multiplied by k, the number of channels that we decided to keep. The best performing classifier is the sample vector machine, but this kind of different results across classifier is quite normal in a real analytics scenario where one would optimize the classifier for the specific task. Here, actually, each classifier was left in its default mode, since, as mentioned, this is more of a proof of concept test, and we are not aiming at the best possible performance on this specific data, but just to find the right direction for further development. And looking at the results so far, we were pretty satisfied, and we felt like we had something in our hands to further develop. And then, since this was, as mentioned, a proof of concept experiment, we also wanted to test some of the assumptions that we based our design upon. For instance, here you see that we project in 2 dimensions the training and the test trial vectors to verify whether the feature extraction model is actually learning something in terms of separation of the 2 classes. Of course, what you see here is affected by the further dimensionality reduction. In the first part on the left, you have a PCA, while in the right part, you have a t-SNE embedding representation. Of course, we are still reducing the dimensionality, so that is a point to consider. But we can see that the 2 classes actually are somehow quite well separated, both on training, and especially what is relevant is that they are separated also on the test subject. So it is somehow transferable to new subjects. And then finally, we decided to do also an ablation study, meaning that we wanted to verify the value added by the channel selection module based on the ensemble of the autoencoders to check whether it actually did capture the inter-channel relationships needed to select the most relevant channels. So on the left, you see a table of performance results without the autoencoder-based channel selection. We just picked the top K channels embeddings ranked on the accuracy of each channel-specific 1D CNN. And as you see, the drop in performance from between the left and the right, which is the one that I showed you before, is significant across all classifier. But what is particularly interesting to notice is that the huge reduction in performance moving from all channels to just 5. So of course, by using our channel selection method, we still have a little reduction in performance because we're using less information, but we're still keeping in a, let's say, reasonable range compared to when not using the information, the autoencoder-based channel selection. The drop moves from 0.9 to 0.77, which is very, very large. So in conclusion, what I presented today was our effort to design an algorithm to perform Eeg channel selection in a cross-subject independent way. I hope I conveyed some of the relevant aspects of these algorithms, such as its end-to-end and classifier agnostic nature. But in particular, I'd like to point out a relevant thing, I think, in this particular context, which is the fact that Ernest actually restricts, even though it is based on apparently complex models, it restricts all computational complexity to the training phase, while it is extremely fast in embedding new signals by exploiting previously parameterized embedding functions. As it showed a good transferability, in principle, the algorithm would not need further retraining for new subjects. Maybe retraining can be something that happens periodically when a sufficient number of new data comes and might improve results. So the results that we found so far are promising. They paved the way for deepening, at least deepening our research efforts. For example, of course, testing our assumptions on very different EEG decoding tasks that all have their own particular complexities, and of course that would need a bit of tailoring. But since we are satisfied with what we saw so far, we will definitely try and seek for new directions. And then finally, trying also to think about developing a single 1D CNN feature extractor that has somehow what here I call a channel-specific group effect, because since we're a statistician, we have in mind our multi-level effect modeling, and we would like to kind of transfer it to the single 1D CNN. So thank you very much for listening. This is all from my side, and if you have any questions, I'm very happy to answer.
Thank you very much, Michela. Looks like a powerful tool, this one.
Hopefully.
Yeah, hopefully, yeah, really. Let's see if there are questions from the audience. In the meantime, I have a couple. One is, so you didn't mention specific applications, so I think you really can apply this tool to any decoding or classification problem, basically, right?
I mean, in principle, yes. I have to admit that we are not expert in any specific field of EEG decoding. What we did was to work on the theoretical side of things. So actually, in principle, it really just needs signals that are recorded simultaneously, and it needs a predefined task. Of course, then there are complexities that we found and that we learned by doing. Every time that you move from one task to another, the signal preprocessing part sometimes needs some adjustments, and the signal themselves need some adjustments. That is why I'm saying that this is a work in progress, and that so far it is, let's say, a theoretical effort. But yeah, it needs tailoring, but it is a principle and a seminal work that might make sense to deepen. That's it.
Definitely. There's a question from Roberto Guidotti. Roberto, yeah.
Still here. So thank you for the talk. I think it's really interesting, and also, I mean, I'm a fan of autoencoders, so I think that it's a very useful technique. So I was wondering if you find some meaningful information in the CNN filters. I mean, if there are some readings that are filtered by those CNN filters. By inspecting the shape of the CNN kernel or filter, as you.
Yeah. So the point is that I didn't show any, because the problem is, as I was saying, that we are waiting to have a more expert eye on the results before we can say they actually are meaningful. So we could base ourselves on what a statistician can judge from the kind of results that we obtained. So basically, yeah, there are some peaks that might mean something, but we really didn't feel like we could say that we obtained something specific, because we don't have the specific knowledge to do that. But actually, there's also to say that this kind of data was pretty simple, let's say. It's more of a toy data set to prove our concepts. So what we found was not really enthusiastic.
No, I mean, I have another question. Maybe it's if you have some intuition about how the trial length affects the classification, if with short trials. I mean, the question is how is the minimum length of the trial that you need to.
Okay, I got you. Honestly, I don't think that the length is a problem. For this kind of models, it is much more important, of course, to have many trials to see. But actually, the length of the sequence doesn't really affect much, because you can just tailor the shape and the length of the kernels in the filters that would adapt to the length of the signal. So that really, I don't think it's a problem for this kind of
because if there are, I mean, it's linked to the other question. I mean, if you have some, rhythms that, for example, alpha rhythm or fast rhythm or slow rhythms, I mean, you need
different
seems to me, the different kernel, different length of the data to better estimate some other, like.
Actually, what we did for this kind of experiment, even though it is still done in a, let's say, knowledge agnostic way, was to try and optimize also the shape and the size of the kernels. And to do that, we actually sampled randomly signals from all the channels together, and we tried to seek the dimension of the kernel that provided the best accuracy across all the channels. So that, I think, is a way to reply to your question. So basically, if you have different kind of signals, you will end up having different kind of kernels.
Okay, thank you so much.
Oh, thank you for the questions.
Okay, thank you very much. Thank you, Michela.